Hello everyone and welcome. In this video we're going to compute or rather evaluate the sum of the following series. Now the series is defined by the sum as n goes from 1 to infinity of the square root of n squared plus n minus the square root of n squared minus n minus 1. Now finding the sum of a series is equivalent to finding the limit of its sequence of partial sums. So that's what you're going to do. So let's get started. Now we're going to introduce some notation. So we're going to define two sequences. The first sequence, which we call b sub n, is defined by b sub n equals the square root of n squared minus n. And the second one is the sequence of partial sums of our series. So it's s sub n equals the sum as k goes from 1 to n of the square root of k squared plus k minus the square root of k squared minus k minus 1. Now the goal here is to find a relationship between s sub n and b sub n. Okay, so we're going to compute b sub n plus 1. This, by definition, is equal to the square root of n plus 1 squared minus n plus 1. Now, after expanding, we get that this is equal to the square root of n squared plus 2n plus 1 minus n minus 1. Of course, plus 1 minus 1 is 0, and 2n minus n is just plus n. So we get that b sub n plus 1 is equal to the square root of n squared plus n. So now we can express s sub n in terms of the sequence b. Okay, so we have that s sub n is equal to the sum as k goes from 1 to n of b sub k plus 1 minus b sub k minus 1. So notice that b sub k and b sub k plus 1 are actually consecutive terms of the sequence b sub n. Therefore, we have a telescoping sum in this sequence of partial sums. Okay, so let's simplify this. Okay, so we can do it step by step. So I'm going to split the sum into three sums. So s sub n is equal to the sum as k goes from 1 to n of b sub k plus 1 minus the sum as k goes from 1 to n of b sub k minus the sum as k goes from 1 to n of 1. Okay, so we can rearrange the first sum, because if we rearrange it, if we write every term of this sum, the first term is going to be b sub 2 and then b sub 3 all the way to b sub n plus 1. So this is exactly the sum as k goes from 2 to n plus 1 of b sub k. The second sum does not change. The third sum, now we are adding ones exactly n times. So this is equal to negative n. Okay, now let's look at the two sums that remain. Now these two sums have everything in common except for b sub n plus 1 and b sub 1. So those are the only terms that will be remaining after subtracting. So we get that s sub n is equal to b sub n plus 1 minus b sub 1 minus n. Now, remember that b sub n is square root of n squared minus n. Therefore, b sub 1 is 0. And we saw that b sub n was square root of n squared plus n. So s sub n is just the square root of n squared plus n minus n. Now, we want to rewrite s sub n in a way that can be used to compute its limit. Okay, so we want to multiply s sub n and divide it by the same quantity. And that quantity is its conjugate. So the conjugate of square root of n squared plus n minus n is the square root of n squared plus n. So we multiply and divide by the same quantity. Now what we do is FOIL the numerator. So we get that s sub n is equal to the square root of n squared plus n squared minus n squared over square root of n squared plus n plus n. Okay, now the square root of a number squared always gives back the radicand. So we get that s sub n is equal to the radicand, which is n squared plus n minus n squared over square root of n squared plus n plus n. Then the n squared in the numerator can cancel out. So they can be canceled out because they have opposite signs. So s sub n equals n over square root of n squared plus n plus n. Now, I want to factor out n squared in the radical. So instead of the radical, we factor out n squared. So we have that s sub n equals n over square root of n squared times 1 plus 1 over n and then plus n. Using a property of radicals, so the square root of a product being the product of square roots, we get that this is equal to n over square root of n squared, which is n. So n times square root of 1 plus 1 over n plus n. And then, because this is a fraction, we can divide or multiply the numerator and the denominator by the same quantity as long as that quantity is not 0. So if you multiply the numerator and the denominator by 1 over n, we get that s sub n is equal to 1 over square root of 1 plus 1 over n plus 1. Now, this expression can be used to compute the limit of s sub n. Now, notice that 1 over n tends to 0 as n tends to infinity. So we deduce that the sequence of partial sum converges to 1/2. So the limit of s sub n, as n tends to infinity, is equal to 1/2. Now, remember at the beginning I said that the sum of the series is equal to the limit, if it exists, of its sequence of partial sums. So the sum of the series is exactly 1/2. So I think this is a good place to stop.